All right, kids. Section 12.1, day 2 is a significance test for B1. Of course, that's from mu of y is equal to the initial beta value, which is the y-intercept, plus b1 times x. I really do wish we just wrote that as a plus bx. It bothers me. This is inference again for linear regression. That's how we started the day out yesterday. These notes are going to be a lot easier for you guys to get through because we did all of the theory background work on the sampling distribution yesterday. Now we can just hammer right through this. So inference procedure number 1 we covered yesterday is the confidence interval. Okay, and that is to estimate an unknown slope of a true regression line for a whole population scatter plot. Inference procedure number 2 is the significance test. And that will be about a suggested mean. Now, I'm going to tell you that almost always the hoe will be that the slope is 0. Almost always. The significance test for the hoe being the slope is 0. So that's basically suggesting, what I mean by that is there is no linear association or relationship. It's not linear. Association. Did I get that right? I think so. Okay. Once you check the 5 conditions, they're the exact same 5 conditions. You need to find a test statistic and a p-value. Now, I'm going to tell you, I'm going to give you the formulas for these things. You're hardly ever going to use them. You're going to get them from those printouts. The test statistic goes, the t statistic is the slope that I get from my sample minus the null hypothesis slope, which is usually 0. So let's just put that in there. Usually 0. And it'll be over the standard error for that slope. Okay, for the p-value, of course, you use a TCDF with n minus 2 degrees of freedom. Your null hypothesis, is the third time I'm saying it on this page, is always going to be that the slope is equal to 0, meaning there is no linear relationship. The ha could be that the slope is less than 0 if a negative association is expected, or it could be that the slope is greater than 0 if we expect a positive association, or we're just saying, no, there is actually some kind of a slope going on. It's not 0. So let's just jump right in and we'll see a significance test. I'm on page 783, and there's definitely a picture of an ugly person. Man, keep that kid in the house. You know what I mean? Infants who cry easily may be more easily stimulated than others. Okay, if they cry easy, they may be people who, have outside world perception better than the others. This might be a sign of higher IQ. So if you got a crying baby, at least you can say, hey, my kid's smart. Child development research has explored the relationship between the crying of infants 4 to 10 days old and their later IQ test. Well, this is my kind of example right here. A snap of the rubber band on the sole of the foot of a 4-year-old baby caused the infants to cry. Now we're doing some science, people. The researchers recorded the crying and measured its intensity by the number of peaks and wails in the most active 20 seconds. They later measured the children's IQ at the age of 3 using the Stanford-Binet IQ test. The table contains data from a random sample of 38 infants. Oh yeah, this is science at its best right here. Let's snap up some kids with some rubber bands and watch them cry. So here's their cry count, and there's their IQ score. I would suggest that cry count is the explanatory variable, and IQ is the response variable later on, right? Okay, so you got a bunch of data points. We don't need to make no scatter plots. They'll be given to us in this chapter. We did that in chapter 3. So here's a scatter plot. Here's the residual plot. And there's the histogram of the residuals. The exact same setup that you guys got yesterday. So by looking at this scatter plot, we can say that it appears to be a weak positive linear association. We can look at the residual plot and see that there's a pretty fairly similar amount of variance. The equal variances condition is okay. It also doesn't show any pattern, which further illustrates that it's a linear association. And this almost looks normal, so it definitely doesn't show any skew or outliers. So our equation would be y equals 91.268 plus 1.4929x. There's our standard deviation of the residuals. That's r squared. If we take the square root of 20, let's see, that's going to be 3 points, 4 points something. So it's like a 0.04 as a correlation, and that means it's pretty close to being 0. Here we go. We're going to test. The null hypothesis is the slope is 0. The alternate is that it's greater than 0 because we think we see a positive association. Then they tell you what the population and the parameter kind of are right here, where B1 is the slope of the regression line relating Y is the IQ score and X is the count of crying peaks in the population of infants, and we'll use a Jesus fish of 0.05. Now look, we should do this every time we start these write-ups. We should say what Y is, we should say what X is, so we get the relationship we're doing a test about. Linear, the scatter plot shows a linear relationship between crying peaks and IQ, and there are no leftover curved patterns in the residual plot. So we think it's linear, even though it's weak. Independent, 38 is less than 10% of all the infants since we did take a sample without replacement from a population. The normal condition, we go to the histogram of the residuals, and we say it doesn't show strong skewness or clear outliers. In fact, it's almost normal. The equal standard deviations, I keep saying equal variances. I think we're talking the same language here. The residual plot shows a fairly equal amount of vertical spread. How do they say it? A fairly equal amount of scatter about the horizontal line. Scatter about the horizontal line. I kind of prefer to say we see a similar amount of vertical scatter throughout the plot. Either way is going to be okay. Random, we took a random sample of 38 infants. Now, for the t statistic, it's given to you right here. So that top line is for the y-intercept, and the bottom line is for the slope. So when you go across, there's your standard error. Here's your t statistic, and there is your p-value. So the p-value is 3.07, and the p-value is 0.004. Now look what they did here. They divided by 2. Now why did they divide by 2? Because when they put a p-value here, they always, in this printout, they assume that this was not equal to. Because back in the day, it was always not equal to. You never put greater than or less than when I started teaching this class. So if we're going to go with a directional alternate hypothesis, you have to take this number and you have to divide it by 2. It has been multiplied by 2. So when I do that, I actually get 0.002. The p-value is even smaller because it's focused on just one tail. Conclusion? Because the p-value is smaller than 0.05, we reject the null hypothesis, which was that it's equal to 0 and there's no linear relationship. There is convincing evidence of a positive linear relationship between cry count of crying peaks and IQ score in the population of infants. That's it, man. That's the whole test. You guys just you just looked at a whole significance test. So what are we doing in notes today? Look, I made a little outline for you guys for how to write up your confidence intervals and your significance tests. And I'm going to do one of each, and that's our notes for today. All right, so let's go to page 788. Now, in 788, that's the actual homework here. What the book's doing is on, what did I say? I said 5, 7, and 9. On 5, it kind of describes the thing and says, hey, check the conditions. And then on number 7, it says, okay, here's the printout. Let's find some estimates for slope and intercept and stuff like that. And then on number 9, it asks you piece by piece the write-up. So we're just going to go and do the whole write-up. We don't need no 3 different problems. We're grown-up, best and the brightest AP stat students. Beer and blood alcohol content. How well does the number of beers a person drinks predict his or her blood alcohol content? 16 volunteers aged 21 or older with an initial blood alcohol content of 0 took part in a study to find out. Each volunteer drank a randomly assigned number of cans of beer. 30 minutes later, a police officer measured their blood alcohol content. A least squares regression analysis was performed on the data using X as the number of beers and Y is the blood alcohol content. Here is a residual plot and a histogram of the residuals. Check whether conditions for performing inference have been met. Okay, so I'm not going to check the conditions right now because we're going to make that part of the write-up. You get to number 7, it says go back to exercise 5. I don't know if you guys can see this or not. I got a lamp in the way. Sorry about that. Here is computer output from the least squares regression analysis of the beer and blood alcohol content. So I have the constant, I have the slope. This right here would be the standard error of the slope, which I would use if I needed to get a t-statistic, but I don't need to get a t-statistic because they gave me one, 7.84, and then they gave me a p-value, but remember, that's if my null hypothesis is 0 and my alternate hypothesis is not equal to. What we're looking for, we'll see it in number 9, I guess. Find the critical value for a 99% confidence interval. Oh, we're not doing a test, we're doing a confidence interval. Interpret the interval. Explain the meaning of 99% confident. Okay, so we're going to take all this. We're going to make a 99% confidence interval. Here we go. Am I in your screen? I think I'm in your screen. There you go. Let's go. We will construct a 99% confidence interval. For the slope of the true regression line. Now, again, I should say what y is and what x is, right? So it's the slope of the true regression line. Now I'm going to say when y equals blood alcohol content and x equals number of beers drunk by these volunteers, these 21 years and older volunteers. Okay, now I should, let's see, I got the idea of the relationship here, and I'm going to do a 99% confidence interval, so I should go right into I'm losing the word for it, the conditions. Ooh, that was rough. Okay, so I'll put a L here for linear. You don't have to do this in your write-up. I'm just going to point out as I'm writing is what condition I'm doing. I was given a residual plot and a histogram, right? Let me bring the book in here for a second. I wasn't given a scatter plot. I was given a residual plot and a histogram of residuals. Well, I can't tell from that the shape of the scatter plot, but I can tell from this that since it's uniform scatter, two things. It is a linear form, and the equal variances is okay when I get there. And now look at this. I don't see any skew or outliers. It doesn't look perfectly normal. If that was over here, it would, though. So that's pretty good as far as I'm concerned. So here we go. Let's rip through some conditions. The residual plot shows no pattern. So the form is linear. Okay. Now we got to use the word liner, right? Isn't that how we do our conditions? So I got L. I is for the independent condition. Now we did sample 21 volunteers here, right? So they were put in a study and they were randomly put into these assignments. So we're talking about this independent condition. Here's what I'm going to write. The subject's blood alcohol content should not affect each other. What we've learned in studying it this year, something new in our text, and apparently is going on in the AP exam also, is that if it's not a random assignment from a population where you're just getting information, if you're taking subjects and randomly assigning them, you're assigning everybody from your subject group. You don't have to do the 10% condition. Okay, so that was the independent condition. Now I'm on to N for the normal condition. The histogram of residuals shows no skew or outliers. Oops. Definitely spelled that right. That's a T and that's an L. My bad. So we're good with the normal condition. Where are my equal variances? The residual plot shows similar vertical distances throughout the plot. So there's a similar scatter for the y variable throughout the plot, any way you want to write that. And then R, the subjects were randomly assigned numbers of beer. Number of beers. Okay, so that's the lion's share of this problem, is just getting through all 5 of those conditions, right? Our confidence interval is, all right, we go B sub 1 plus or minus T star times the standard error of B1. You got to look up the T star, okay? The degrees of freedom are N minus 2. And so how many volunteers did I have? I had 16. So the degrees of freedom is 14. You subtract 2. So I go and I'll bring the book over here so you can see it one more time. I go find my slope. It is not the constant. It is the one that's got a name. It's 0.017964. What should we put for that? Probably 0.018, right? So I'm going to go 0.018 plus or minus degrees of freedom 14, 99% confidence interval. I looked it up in the chart. It's 2.977. And the standard error for the slope is, once again, there's the slope. The standard error is 1 over. It's 0.0024. So I put in times 0.0024. I put this all in my calculator, and I got 0.01 to 0.025. Notice 0 is not in that confidence interval. I am 99% confident that there is actually a slope that's not 0. There's a linear relationship. So I'm just going to write, we are 99% confident that the slope of the true regression line, and what I mean by slope of the true regression line is I'm referring to the population scatter plot, right? The true regression line where y equals blood alcohol content and x equals number of beers. Seems to me that it's reasonable to say if you drink more beer, you're going to have higher blood alcohol content, so this slope should be bigger than 1, is between, of course, none of you would know anything about that. That's good. 0.01 and I don't know why I just put that in parentheses, and 0.025. Okay, there you go. There's your confidence interval. I know we covered that yesterday, but I thought it would be good to see you guys, to have you guys see me do a whole write-up. So I got one more thing to do here today. We're going to do a significance test. So go to 791, and we'll go to number 16, and we'll do a significance test, and that'll be it for today. Time at the table. Does how long young children remain at the lunch table help predict how much they eat? Here are data on a random sample of 20 toddlers observed over several months. That's what I really want to do with my life, is go observe little toddlers eating food. That's just a party right there. Time is the average number of minutes a child spent at the table when the lunch was served. Calories is the average number of calories the child consumed during lunch, calculated from careful observation of what the child ate each day. Okay, thank you for telling me that. So time is the explanatory variable. Calories is the response variable. Here's some computer output from least squares regression analysis. So there's the computer output. I've been given the scatter plot, which looks like it looks linear to me, like a weak negative linear association. The residuals show no pattern, and the variation is pretty similar throughout. There is a dot plot of the residuals, and I don't see, it's almost like they're all dots all over the place. There's one that's stacked. I don't see any skew or outliers here. So we should get through, once again, the conditions pretty quickly. Okay, here we go. Let me find my answers. We will perform a significance test at the level. Now it does say in here somewhere, if you look for it, you'll see it, 0.01. It did change the significance level from 0.05 on the following hypotheses. Now I didn't start with a population. I'm just saying what I'm doing, and then I'll get back to it. The hoe is that b is equal to 0, and if you read that problem carefully, the ha, it just says, is wondering if it's different. So this is actually going to be b is not equal to 0. Okay, here's where I bring sort of the population in, or the story, where y equals calories consumed. And x equals time at the table. Okay, so I should probably put for toddlers, right? There we go. How do you spell toddlers? It's definitely okay. That's toddlers. Now, for the linear condition, the scatter plot looks like a. here, how should I write this? The scatter plot shows a weak negative linear form. A weak negative linear form. If you guys got your book open, you can take a look at it. It looks weak, it looks negative, and it definitely looks linear. For the independent condition, this was a situation where we did actually randomly select toddlers and observe them. It wasn't an experiment where we randomly assigned them. So, how many toddlers how many little brats did we talk about here? 20 of them. The n equals 20 toddlers. I have no idea how to spell that word. Is it two D's, toddlers, or is it just one D? I'm not sure that I care. You know what? I could just read it. It's in the book. It's two D's. I'm sorry. The n is less than 10% of the population. Okay, so that is, let's see, we've got the L, the linear condition, and I, the independent condition. N is next. For the normal condition, what did we have? We had a dot plot. The dot plot of residuals. The dot plot of residuals shows no skew or outliers. All right, there's the normal condition. LIN, I'm on E, equal variances. For the, or I'll do it like they do, for the equal SD, for standard deviation condition, the residual plot shows similar vertical spread throughout the plot. Okay, and then we got one more, random. What am I doing these? We had a random sample of these 20 brats. So the 20 toddlers. Did I really have trouble spelling toddlers earlier? What is going on? I just did it again. I spelled toddlers. It's a good thing I don't have kids. The 20 toddlers were randomly selected. Let's just imagine what that kid would be like right now. All right. There. I'm done with my conditions. So now I would use formulas, but I don't need to because I'm given everything I need in the problem. Let me bring this book over here one more time. And you see, this was the one about the toddlers, and there's the time at the table. It's a little different than I thought. The longer they sit there, the less they eat. I guess they're just being brats and sitting there and being stubborn, right? I guess that's what we're talking about. But now I'm down here. There's the constant is the y-intercept, and this one's going to be the slope. That's the standard error for the slope if I needed to put the formula together, but I don't because I have a t statistic of negative 3.2 and I have a p-value of 0.002. That's if my alternate hypothesis is not equal to. If I had an alternate hypothesis that was greater than, or I had an alternate hypothesis that was less than, I'd have to divide that by 2. But I don't because mine is actually not equal to. So here we go. I'm just going to write up what they gave me here. Our t statistic and p-value are t equals negative 3.62. I'm just going to say from the printout. Like I would want you to put that if you were taking the AP exam, right? And the p-value, or I can just say NP equals 0.002. Here we go. Since p is less than 0.05, we reject the null hypothesis, which was that there is no slope, and conclude that there is a linear relationship, meaning the slope is not equal to 0. There is a slope, right? There is a linear relationship between time spent. I'm going to leave out at the table by toddlers because clearly I can't spell the word toddlers, and calories consumed. Toddlers. I spelled it right. Look at that. There's always room to grow, guys. There's always room to grow. You can be a better person. Look, I just showed it. Let's see. That's it. That's it. We're done. So I think that I should look up a couple of problems from the book for you guys to do a couple of write-ups here. And that's good. I'm going to pick one of each. And if you guys wanted to, you could do more. But I'll put on Canvas one of each of these last two problems. And that's your homework for today. Have a good day.